All right. So Max has mentioned that he's happy for people to interject with questions during the presentation. So if you'd like to do that, you can do so. If not, you can put it in the chat box. And I think I've pasted some helpful links there as well, connecting to our LinkedIn page and to our mailing list. So yeah, just have a go in the chat box. And alternatively, if you just want it to be a private question, you can email it to me. All right, so there are one or two new people like myself here. So I might start with a brief introduction about these talks. So this is the second CARES Commercialization Talk of 2022. This series was started by Nick and Zhen, who are both here today. They thought it would be useful to have a space where researchers who are planning to commercialize their work could connect and learn more from one another. And it is my pleasure today to introduce today's speaker, Dr. Maxilian Moser. He is the CTO and co-founder of Biosimo Chemicals, a bio-based platform chemical startup. Max concluded his doctoral studies on the topic of halogen recovery via catalytic oxidation and moved into a project leader and consultancy role for the Boston Consulting Group in the chemical and pharmaceutical industry before co-founding Biosimo Chemicals. I'm sure this will be particularly exciting for attendees who are looking at opportunities outside of academia. So yeah, thank you, Max. Over to you.
Thank you, Olivia. Thank you for the kind introduction. And yes, welcome everybody. I'm super excited to be here today, speak to you on behalf of the team at Biosimo about sustainable biochemicals, a topic we have been following for a couple of years and really starts to get more and more traction in the last months, in the last 2 years, as the whole economy, the world, everybody really wants to push more towards sustainable solutions, be it in energy or in materials. And as Olivia just mentioned, we are a medium classroom size group today. So I have the chat box open here in the bottom. And what I will do is I will go through the presentation. And if questions arise, I will have a little look at the chat. And I will then stop at the given point and answer these questions. But also, I have planned for a little Q&A session in the back for questions that might arise that might not be on topic at the given point. So no worries about this. I will try to answer everything that you want to know. Now, looking at the next hour that we have planned, I want to give you quickly a first brief overview of what we actually are, so who and what is Biosimo, so you have an understanding what we're doing, what we're set up with. And then I have today's talk structured in 3 sections. The first is I want to briefly talk about the opportunity for sustainable chemicals. That might be a topic that you could be very aware of, maybe not already. And I want to talk about how we perceived it. Then the core of the presentation is about how to approach commercialization. This is going to be from our perspective also at Biosimo. It's heavily influenced by our experience, and I will try to practically give you an idea of what are the important things that we have started to consider, what were the hard lessons we have learned and how we approach that. And the last one, 10 minutes, is a bit about the mindset shift from academia to startup. And this is also something often underestimated, that it's not only about what you do, it's also how you do it and how you approach it. And then I said in the end, we can do a little Q&A and discussion session if you like. Now let's jump in. Biosimo chemicals. So what we try to solve is, as introduced, we want to make sustainable chemicals. And the problem that we try to solve is that in today's industry, most chemicals that we are using in manufacturing are practically based on fossils. Like, for example, our product that we're currently pursuing, our first beachhead, acetic acid, is 80% gas, 15% coal, and only 5% is made from biomass. The total amount of carbon, if you take this together, would equivalent up to 26 million tons of CO2 equivalent emissions if you just look at the fossil compound. And also, acetic acid is one of those chemicals that you cannot easily recycle. So it's used, for example, for perfume, for pharmaceuticals, or in the treatment of textiles. All applications where acetic acid will dissipate or will be basically changed to the state that you cannot recover it easily. And so you have to regenerate, you have to make new acetic acid all the time. Now, our solution to bring a larger quantity of bio-based acetic acid to the market was for the catalyzed oxidation of bioethanol, which has a higher potential for a higher capacity and a higher cost effectiveness compared to current state-of-the-art enzyme systems, which are limited, of course, by their complexity, but also by the higher cost associated with them. And in the course of this startup and how we build it up, we were supported now through a very broad network within Switzerland, stretching from organizations like VentureKick, the Gebert Rüft Stiftung, Bridge, which is part of the Swiss government scientific funding, the SNF, similar to any other national funding, science funding organizations, and of course ETH Zurich, where we're still located. So we are right now not in our own, let's say, building or research facility yet. We're still using our labs and offices within the university that we have received from them, from where we are right now driving the startup. Now, who is that team right now? Before I introduce myself, this is of course Dr. Sotiria Mostro. Sotiria, who is our founder and CEO. She was the principal investigator on the technology and has driven the early development. She has now taken on the role as a CEO, driving our investor relations, driving the strategy. Then there's myself, is Maxilian Moser. I'm the CTO and founder of Biosimo as well. I have, together with Sotiria, developed the business plan. We have worked on the technology. I have a background in consulting, but I'm also very passionate about technology. So when we did, let's say, a formal split between responsibilities, I was very happy to take on the CTO role, also driving commercialization, because during my tenure as a PhD, but also before and after, I was working for chemical companies, and I have been working also in the commercialization of processes for the halogen recovery that Olivia mentioned before. And then we have, of course, two further colleagues. One is Konstantina. She is our product chemist. She's our lead in the lab now. She has taken over lab operations. She's running reactions. She is head of our quality assessment. She is, for example, driving that we are establishing the right methods to measure and ensure the quality of our product for our customers. She's also helping to develop methods for the further process development regarding process purification systems and the like. And then Dominic is our current business developer intern. He has a background in business. He has been working strongly on strengthening our business case, deep diving into our strategy, and helping us also flesh out our strategy for the next 12 to 18 months. And George here on the right side, I don't have a picture of him yet because he's quite shy. He's our laboratory assistant, student assistant. He has joined our team just recently, and he's supporting us in the lab, making catalysts. Everybody who knows, if you make catalyst, you need to crush and sieve and powder a lot of material. So he's helping with that. He's very motivated and great. Then on the expert side, or exactly in our ecosystem, we have already a couple of committed advisors like Anil, like Alicia, like Harun and Stavros, that bring their own expertise into our startup and help us, for example, grow, work on our weaknesses and help us play on our strengths. For example, Anil has been an entrepreneur. He is a lecturer of ETH. He's helping us really driving the way how we have to organize the business. Because for us, that's also the first time we do a startup. So we also need to learn, for example, how to run a board meeting. The same with Alicia. She's an experienced entrepreneur and marketer. She helps us working on our self-branding, on how we should, enter the market and coaches us also on these aspects. Then Harun, he's Sotiria's former advisor and group leader. He's hosting us in his labs. He has been very helpful in advising us on R&D. And Stavros has been also from a lecturer of mine and Sotiria. He's a professor in Vienna for process engineering and process simulation. He's very seminal regarding helping us to scale up the process, giving us advice on where to put efforts, but also helps us understanding costing. So something that you don't know before when you do a lot of academic work is costing for a plant, or what does a pilot plant cost and what to consider. So he helps us really much there. And then on the right side here, We have a bit our business support network, just a few logos to kind of give you the impression that there's a lot of people involved. That stretches from, the ETH technology transfer, that's our university entrepreneurship center that also you will have in Singapore at Cambridge. Then we have Lexa or Prince. These are our lawyers that help us with setting up the legal things, but also the patents. We have Sential, who helps us, for example, on the marketing side or making materials, because one thing that you have to realize after working for 5 to 6 years in academia, there's not many people who understand chemistry, also on the investor side. So you need to really start working on how you sell your chemistry, especially if you do deep tech, to people that have absolutely no idea what a molecule is. Of course, BCG has been also helping us with that, doing some market analysis. And as mentioned before in the slide, our accelerator and funding network that has helped us building the business so far. Now, let's talk about the opportunities of sustainable chemicals. So something that people kind of know but always underestimate is the sheer size of the chemical industry. So right now in 2020 is the latest numbers I could find. We're talking about 3.5 trillion euros or US dollars, more or less the same right now, of value for the chemical industry globally. And the largest piece of this is in China, but also US, Europe, and the rest of Asia has a huge contribution to this. Chemical industry is really a huge sector, and it cannot be underestimated its impact on our environment, be it through emissions, but also for the materials that we use for it. As a matter of fact, when you look into value add, so when you take raw material and then you make something out of it until you reach a product, each step adds value to the product until it comes out. For example, if you have an iPhone in your hand, mining the ore, smelting the metal, forming it into a frame, and then actually putting the components together to a phone, every step adds value and has a value creation step. And the chemical part or chemicals itself is the highest value add that we do as a civilization, I must say, to our goods and products. So addressing environmental and sustainability efforts within our material flow chains has to really target chemicals above all. And it's the most important part of our manufacturing. However, right now, up to 85 up to 90% of the chemicals that we use today are made from fossil sources, mostly oil. A large chunk comes from gas, and then there's also a certain part of coal. Now this circle on the right is a generalization across the whole industry, but this changes rapidly depending what chemical you look at. And there are base chemicals, for example, where you will have almost zero recycling and almost zero bio content and a very large chunk of coal. And then there are other chemicals where you have, for example, a natural resource that you can exploit for making it, which will also increase the share. But overall, this is roughly what we're looking at between 2015 and 2020 for a share of our chemicals, which means 450 million tons of carbon a year are embedded into these materials, and 85% of these come from fossils. Now, this is a big issue because we cannot recover and recycle everything. So by introducing so much fossil carbon into our material supply chains, we also increase the amount of anthropogenic carbon and CO2 eventually in our environment, because it is actually additional carbon that we bring into our nature. Now, pollution has already driven the end consumer to look for more sustainable products, and people have recognized this problems now for many, many years. I mean, pollution reports range back 50, 60, 70 years. It's not that we are only aware since 2000 about the climate change problem. It reaches back much further. And consumers already say, if I can make a difference, I want to make one. 96% of consumers say they want to make a difference. They want to buy, for example, sustainable packaging, which is rapidly growing, and companies address this. 85% of the companies have a sustainability strategy where they, in one way or another, commit to certain emission targets or reducing the waste, or they're reducing the amount of fossil input that they need. However, it's not that easy to actually achieve that, even if it sounds easy, because one thing that consumers also want is they want to have their products and they want them cheap. So if you, for example, launch a new bio product or new biomaterial for a bag or anything, you often can't preserve the same quality standards as, for example, other materials just because it deteriorates faster. Or you have way too high cost to manufacture it. So the amount of people that can afford it or the market you can address is very small. And at the same time, you have very long development lifetimes to actually get to a product. One product, and I think it's the biggest success story that we really want to emulate when we look at the bio-based chemical or sustainable chemical market, is Coca-Cola's plant bottle. I don't know if everybody knows, but back in 2009, Coca-Cola was talking about, okay, how can we reduce our carbon footprint, our anthropogenic carbon footprint by reducing the amount of waste. So they were actually starting to look at if we can use different plastics for making bottles, because back then they only had PET. And what turned out to be a lot of research, they figured out they cannot find a bioplastic that they can use for replacing PET, because no other bioplastic kept the CO2 of the carbonated drinks inside the bottle. Most bioplastics were too permeable. The CO2 would simply diffuse through the plastic, and the drink would become stale very fast. So they couldn't do it. So what instead they did is to say, okay, if we can't replace PET, let's make PET green. So they funded a lot of research in the last 10 years to the point to understand, okay, what do we need to make PET green with? So they looked at the molecules that are required, like monoethyl glycol and the other components of PET, and successfully made one after the other of these molecules green together with their research and development partners, up to the point now that they can actually offer in the market 100% plant-based bottle that is made without using oil, gas, or coal as a starting material to make this plastic. We still get the same property for the material, we still pay the same price for it, but the impact that we deliver for the environment is huge for that. And it's a great success story that many people now try to emulate, including us. And this is practically then in telling you, this is practically now addressing to that. So what Coca-Cola was doing is they were looking at the plastic already. So they were already looking at higher value chemicals and around the specialty chemicals, which you need as monomers for making certain plastics. But what we are trying to do at Biosimo is we want to get one step earlier. We want to look at the bulk chemicals. There are about 10 to 30 chemicals, platform chemicals, bulk chemicals, commodity chemicals, as they're usually called. Starting from ethylene down to acetic acid and others that practically form the basis of our economy. And the ambition that we have is to say, if we can manage to make those bulk chemicals green, we successfully could also make all the other chemicals down the line more greener or even completely green in the process, without having actually to switch our supply chains, without actually having to change the quality of the products, and more importantly, without raising costs. Because one thing that mentioned before is it's not only about being sustainable. Since we are working in a global market, we also have to watch cost, because this is a key driver for the end consumer to adapt to new materials, and you want that they adapt to new materials. So that's very key, that we can figure out how to make bulk chemicals green. Now, what kind of resource should be used for bulk chemicals? I've mentioned now bio-based, but that's not the only source we can use. Depending, and refer to the circle I showed before, there's also recycling. And right now it's not too prominent, but it's expected to become very prominent. There's the use of CO2 as a raw material to make chemicals. These three buckets together ideally should form the basis of our chemical industry in 30 years, which is, I use the word now a lot, very ambitious, but it's what we want to try as a society, as a civilization to achieve. Now, why, some people might ask, why do you want to go for bio-based if you can make everything from CO2 or recycle? Well, that's not too easy. So there is certain limitations, of course, to where you can use CO2 and also can use recycling. So not every material can be recycled, as I mentioned before. There are chemicals, for example, again, the example acetic acid, where you use it, for example, for paints and glues, where the chemical dissipates or it isn't recoverable. Also for perfume or pharmaceuticals, you can't recover that. It practically dissipates into our environment. And then again, CO2 is a good starting material for many chemicals, but again, it's right now very expensive. It will stay expensive, and also it is already a strongly oxidized monocarbon. So it might not be the best way of starting a chemical supply for every material. It will depend strongly on where you are on the planet, where you can use CO2 as a starting material or not. That will be always the truth. So in the end, biomass or bio-based chemicals will fill in a gap where you can't use recycling to 100% and where you can't utilize CO2 to the most effective as possible. And it also, biomass is something which is very favorable because it's a regional source. Almost every country, actually every country, every continent has biomass to a certain extent that you can use to make chemicals. One reason why we have global competitions and also inequality in between regions is because of our access to oil and gas. I mean, it's very evident to most of us that we have fought many wars over oil and gas in the past 150 years as a civilization. So making chemicals from biomass also de-risks a bit the issue of being dependent on oil and gas, but also helps countries that don't have access to these resources to really build up an own chemical supply chain in the future. Now, let me quickly switch a bit more deeper than in the acetic acid part, because this is the one I can talk most confident about. So I mentioned before, acetic acid, broad application. Many of these applications difficult to recycle. Cellulose acetate here on the bottom right, one of them you can recycle the best because it's still a plastic. But then you look at paints and glues, or for example, food additives, it becomes more difficult. So there's always a need to replenish this chemical in a certain way. As I said, we're looking at the chart of bio-based acetic acid, and it's still a lot of gas and coal, loose, very small as biomass. So we asked our customers, for example, okay, what do you see in the market? What do you want? And we really hear three replies to our questions. The first one is, I cannot find enough bioacetic acid to complete my demand. So we have customers in the market, companies that say we want to use it, we can't get it. It's just too scarce. Or it's too expensive. Right now, in new bio-based, the one we have from biomass is mostly fermentation driven. It's 2 to 3 times the price of the fossil. So even if they say it's a nice idea, I cannot economically justify buying it, because it simply is not, it's not possible for them to have that high raw material cost, in particular right now. And then the other thing is that, of course, they say we need the same quality chemical, but in larger volumes. That refers to the fact that it is sometimes difficult to get exactly the quality you need. Something that we always underestimate a bit when we're in academia is purity of chemicals is one of the most important selling factors. And if it's not exactly the same as the fossil, if there are certain other impurities in the product, for example, if it comes from fermentation or from biomass in that sense, it might be that you don't consider it massive. It could be 50, 100 ppm of a certain species. It's possible that a certain chemistry is actually inhibited by it, or that a certain catalyst by a customer might be inhibited by it. So there's always these black swans in your impurities that you have to look out for, which can make it difficult for you. Exactly. So then the market for acetic acid is very large. It's about 13 billion. And we really try to drive the biomass up. And we think that the acetic acid market will reach up to 50 billion by the end of the 2050. And the biomass and renewable will take a big share. Personally, we think that there will be fossil-based acetic acid be left in the market. We don't think it will grow. It might decline over the next 30 years as plants become older, and some of them might not become revamped. But in the end, we will still have a mix with fossil and these renewables and bio-based products. Just a quick takeaway from this first part. So chemical industry is the most value-add driver in our society. And there is a real drive to make sustainable chemicals the norm, but there is also a lot of hindrance, mostly cost and availability, that we have to overcome. Now, I hope I didn't speak too fast, but I would say we pivot over into how to commercialize. So we now talked about the market and how big it is and how it would work, but now, how do you go about it? So let's assume you have found the perfect bio-based chemical or sustainable chemical product. The first thing that you will have to do then when you go to your association is you have to talk about, okay, what's the solution, the value proposition I actually have? When you go to the institute or to the patent lawyers, they will ask you this question. So yeah, great technology, great chemical, congratulations, but what do you do with it now? What is the value add? That's the first thing that you have to describe and think about it here. What will you do better with your chemical new process that industry can't emulate? So for example, in our case, we said, look, we do the same chemical, but it's a clean technology. Our process is less toxic than the original industrial process. We want to localize production because in Europe, we don't have big bulk chemical production anymore. Everything was shifted either to the US or China. And we, in that sense, also want to decrease our dependence on fossil supply. And that, of course, are strong arguments that can back your value proposition. And then, of course, you also need an ambitious plan. So here's a bit of a snapshot of what our ambitious plan looks like to go from lab to commercial scale in less than 6 years. If you believe it or not. The important point is that you make clear not only it's too much serious about what the years is that you mentioned here. The point is that you have a clear plan of where you get from what to where. So we did it at a lab in a gram scale. We made gram scale product. We go to the pre-pilot, which will hopefully bring us now kilograms of product. And then we want to build a pilot plant, which brings us tons of product. And each of these scale-up steps is by 1,000. And that in terms of chemistry makes sense. You always go up 1K in dimension until you then reach the commercial small plant. Then you do the last 1K jump to the 50,000 ton plant. That is what you can consider in chemical manufacturing, depending if it's not a specialty or large commodity, a commercial size. For us, since we want to do a bulk chemical, it is a small commercial size. So we would have another step maybe to go to 250,000 ton plant. That is what you could usually recommend and see then for those kind of chemicals as the standard. And along these steps, you always have to do two things. You have to provide a proof of concept for a certain element that you can only prove at that step. That's why you do the scale up, to prove a concept. So for example, we prove first the reaction, then the process, then the scalability, then the profitability. And at the same time, you start de-risking, of course, your technology or your commercialization. So in the beginning, you try to de-risk, for example, does the catalyst work? Does the process work? Can I actually purify the product? That's basically the de-risking you do in the first two steps. And then later you try to de-risk the scale. Do I actually get the same performance if I go up 1,000? Do I get the same performance or even better performance if I go up another 1,000 factor? And once you reach that, you seem to be done. But that's only the R&D piece. One thing that you have to do from the start and that you actually have to solve way before commercialization is de-risking your supply and de-risking your demand. And that's something that is usually not evident sometimes if you come from R&D, because you really much focus on technology, you focus on the scale up, you're looking at the technology scale up, but you need supply and demand discussions from the start to really make sure that you're not missing out the point on what the customer wants. And that brings us practically to the 5 key factors of commercialization that I want to talk to you about today. Supply, technology, demand, as just mentioned, and the 2 fundamental underlying things, which is the team and the funding. If you want to commercialize a technology out of your lab, you really have to have these 5 factors under control and have a plan of how you want to do them. Now, I want to take you through a few examples along the acetic acid development that we have done, starting with the supply. Now, as mentioned before, we are using bioethanol to make acetic acid. So for us, bioethanol is the key supply that we would require. And it's actually a very large product. Bioethanol is the largest bio-based chemical on the market. It's about 100 million tons. And it actually has a problem because 70 to 80% of bioethanol today is used as an additive for gasoline for automotive internal combustion engines. And as you, for example, have been announced in the European Union last week, they want to actually avoid the new registration of internal combustion engines by the year 2035, which practically means all these bioethanol producers have a bit of a problem because their market is going to decline eventually. So they are all looking for new ways of selling their product. And what we are offering them now is to say, look, we can help you use your bioethanol to make chemicals with. And we have already started partnering with bioethanol producers who see this opportunity, because we can offer them, by valorizing ethanol into acetic acid and other products, to actually get a new revenue pool and make sure that they can sustain the business development even past the decline of the internal combustion engine. Now, the second question, of course, is there actually enough bioethanol to make acetic acid and biochemicals? And the very simple answer is yes. So as I mentioned before, it's about 100 million tons globally. In Europe, it's actually only 10% of that. So we only make about 10 million tons, roughly 10 million liters, depends a bit on how you factor in the density. And if we, for example, compare this to our 250 kiloton plant that I just introduced as our commercial large scale, that would be less than 2% of their production. And now if you think about that, the market is still growing at 5 to 6%, then whatever we need to make acetic acid in our proposed plant would be within the growth of that market over year on year. So supply for us is available, and the need for bioethanol producers to work with us is also given. So on our end, we have really secured supply. But if, for example, if you talk to other bio-based chemical startups, for example, those ones who want to work with, let's say not make, but work with biomethanol, or if you want to work with green hydrogen, you will clearly see that prices for these two commodities right now are really high and supply is really short. And at the same time, also the demand for using hydrogen, green hydrogen or biomethanol for other applications is really high, especially for fuel. Biomethanol is supposed to be a good fuel for shipping in the future, which will drag a lot of demand. And green hydrogen, of course, is a future as a fuel, which will also pull a lot of demand into the fuel sector. So the question is, how can we sustain a chemical business in parallel to this if there's a lot of pull into the fuel sector, which will complicate or increase your prices also. These are considerations that you have to bring in. So what is your supply? How do you secure it? And is there, like in our case, is there an intrinsic incentive of the supplier to work with you? Are they basically pushed to you, or do you have to pull them into your business? Now, technology, again, it's the key topic. Most of you are familiar with your own technology, but also there's something that changes a bit once you go from academia to startup. So we are happy because we have our bioethanol supply secured, and then we have, of course, our technology together. We have the IP, the know-how, and the trade secrets. But then also what is important is, and people underestimate, is we also have to have an MVP product. So it's not only enough to say we have created a reaction that works, but you also have to show and demonstrate that you actually get the final product out. So can you make technical grade or glacial acetic acid with your process? Is it possible that if you run a reaction, you actually come to that chemical? So this step from I just did a chemical reaction and it works out and has great yield, to I can actually also purify the product into something I can sell. That's something that also has to become included in your technology. So you have to expand your technology from whatever you've done to also include the final product in the future development. And this is the expense you have to do. And also you have to start banking on your advantages. So from our case, for example, it was the fact that we were the first ones to work with flow chemistry. So we did flow reactor systems for the bioethanol oxidation in a triple flow reactor, which had a higher throughput, allowed us also to screen faster materials. And we, of course, use a metal oxide catalyst, which we can position as cheaper and more stable than the contemporary processes that are existing. Because right now, acetic acid is made from methanol using a homogeneous catalyst, and the fermentation is using certain bacteria and cells, which are much slower and which produce acetic acid at a much lower concentration in water than, for example, we can do. Now, our catalyst system, as I mentioned, has outperformed the gold system. Also, something that's always important that you show, like, what can you do more in respect to to the performance of better production, less byproducts, less CO2 formation, and cheaper. That's basically the 4 things that you want to highlight out of your technology. Everything focused a bit more towards production and how better your yield is. And in the end, one more important thing about when you do your development, you don't have to have the best world-in-class system figured out when you start doing a business. If you have a system that's already above the state of the art, you keep investigating, you keep researching. You will not have the best optimized system that will go into the final plant in the beginning. Actually, it's a nice quote that I've heard recently is, if you're not embarrassed by your first version, you waited too long for the next step. So drive your development, but also be aware of your minimum viable product, your MVP. If the catalyst is good enough to do the next step, like for example, go to the pilot plant, you decide, okay, this is the version I go into the pilot plant of the test, and you keep further researching stability, improvement, etc. You never stop, but you have to make sure that you don't stop yourself from the next step just because you're not 100% clear on that the catalyst is the best. And then talking about the expense for the core technology. When you go from the lab to a process, you will start realizing suddenly that you have much more problems to think about. So on the left-hand side is the scheme of the laboratory reactor with the gas bottles and everything, was very neat and nice. But now when you do a conceptual design for your plant, that whole thing which is here on the left is practically here on the right in this red dash box. So you have a lot of more things to worry about, distillation, extraction, waste streams, how to do heat integration, compressor safety, and that's also things that completely usually then go beyond what you know, and where you definitely should then seek to expand your team and seek third parties to help you design it. Let's look quickly at the demand. Now, when it comes to the demand, one thing that you really need to figure out early, because that's something that investors and companies want to see, is what is the global demand, but also what can you address? So it's always very important that to have you on the right side, that you think about how many clients can you reach? What do the customers tell you what the demand is, so you can start building up bottom up a bit. What kind of demand do you have, so you can also rationalize how big the impact on the industry for you will be. And then of course you have to start thinking about who do you address first. So not every customer needs you to produce 250,000 tons a year. Some of them will start and say, hey, give me a few kilograms. Let me test with my vendor qualification. Let me test your product in my R&D. And that's good because it allows you also very early, when you're still in the lab or in the pilot stage, to sell off small volumes to customers, to create some revenue and create some reputation if your product is good. And that you definitely have to do before you think about customization. That's why reaching out to customers as early enough is important, so you make sure that you get your foot into the door with their R&D or with their procurement especially. Now, when it comes to the team, I've mentioned before, and I've very much explained how we are working together. One thing that is important when you are an R&D team is how do you hire? And that's the one point I actually want to drive here. So hiring is often underestimated. It's a very tedious and time-consuming process, and you're often not trained to do it. And when you talk to different bio startups in the past, there's something that people usually say what the first mistake was, is they hired themselves, they hired their colleagues from this research group, they hired people from the other research groups and institute, and suddenly you don't have a startup, you have a research group within a research group. But what you need is, you need to hire those people that play on your weaknesses that you have to mitigate. For example, process engineering. And you need somebody, not somebody who does academic process engineering, it's somebody who actually has hands-on experience or wants to do hands-on work, somebody who wants to design a pump. So don't hire yourself, but also don't hire B players. You want to hire people that are more independent, that really want to drive. And in that sense, really try to hire also diverse backgrounds, meaning hire people that bring different viewpoints to your technology, that bring different viewpoints to the business, because only though you can double check where you're going and understand if you're on the right path or not. If you're hiring people who are too agreeable with what you're doing yourself, you will very quickly run into issues you could have avoided. And also hire for social fit. You will spend a lot of time with these people in the lab. You will also have situations where something doesn't work. you need to make sure that the people that you can work with you can really stay around. You know, if even if the person is a genius, if he doesn't fit into the team, he will not contribute to the success anymore once things don't work as well. So it's very important that you keep this in mind when you hire. And there's a lot of literature around this that people should really try not underestimate building the team. It's not that straightforward, but it's not undoable. Exactly. And then the last part that I had was, our hiring approach is that we use multiple channels. We plan enough time for hiring. So if you need somebody in 4 months, you should have started last month already. Give yourself 4 to 5 months for hiring. And also something that we do is leverage your advisors to interview people. Just because you're the founder doesn't mean you're the only person that has to interview. Ask your advisors or maybe a professor or somebody to also interview people for your team to make sure you get multiple viewpoints. Never just try to do this alone or only in a team of 2. Get people that help you also to support you in the hiring process. Last but not least, actually the most important point, but funding. Here, I just wanted to give you a quick overview because we could talk another 2 hours about funding. And that is the difference between academic research and startup. So if you're in academic research, if you're a PhD postdoc first year, not if you're a professor, you would have seen more of it. You do 1, maybe 2 grants. You write a big grant, you get your 500,000, 2 million grant from the university or from a national foundation. You're covered for 2-3 years and you're fine. And you do your work and that's good. And if your research is successful or not, it doesn't matter really, because even if you don't find something new, you have proven or unproven a hypothesis and you have contributed to science. It's all okay. However, in startup, it's a bit different. You have to apply up to 6 to 10 different funds and grants per year and engage with investors. And you have to show track record. So you have to prove, okay, so we started here, we're now here. Yes, failure can happen, but you always have to have a plan. And if you're the founder, you will very quickly start spending more time on raising funds and talking to people than actually doing R&D work. And that brings us back to hiring and the team. You really need to think about who is doing the R&D legwork at one point in the company very fast, very soon to support you. Not because you're suddenly too good to do it. No, you can also go back in the lab and make coffee and help and support and run a night shift on the reactor. That doesn't mean you're not doing these things anymore. But you need somebody who becomes more in charge in the lab than you, because you simply won't have the time anymore if you decide to really push the company. Yeah, so takeaways here, technology is really just one of at least five factors to drive commercialization. Really try to engage your suppliers and buyers early enough so you understand their needs and use them also for your grant applications, for your funding, for your storyline, and hire the right people, so that you have enough time to spend time on raising funds that you need, especially in chemistry. It's a very capital intensive business, so you need to really spend time on that. That cannot be underestimated. Now, for the last 5 minutes, just before we go into the Q&A session, mindset shift. So we talked a bit now about some tools and fundamentals, but one thing that I really wanted to stress with you is a bit the mindset shift, because it's something that a pit that we fell in the beginning and that we came out luckily quite fast. This is working in science and startup is not the same. And there's a certain danger of a false sense of routine to it, because one day you walk out, just gotten your PhD diploma, next day you walk in and you have a startup. It's still the same lab, the same workspace, there's the same people around you, and you practically do the same daily routine. But it is not the same. You might still author a paper for something that you want to finish, or you still write an application for conference, but these are all things that are not anymore agreeable with the target of running a startup and building a business. And coming out of this and making the shift in your head that you have to work differently is very important. Because, and I try to very simplify this now here, when you look at the risks that are associated with your R&D work in academia versus a startup, it's on the different end of the spectrum. In academia, you're practically down in the singularity, this little point down here. You practically have no risk. Once you have a research grant and the grant extends to the end of your PhD, you're covered. You do your research, it can be successful, not successful. You will do good work, you will get your degree, everything is good, and you will find a postdoc later. Return here in terms of financial, let's say, or success of the commercialization is also very limited, because you're not working for that. You're working for science. You're working for creating knowledge. Yeah? So no matter what you do, if you do good science, even if it works, doesn't work, you will contribute to academia. You will contribute to knowledge. Now, in startups, it's different, because you are burning money. You don't have a lot of return in the beginning. You need to make sure that you hit your milestone so you can get more funds to reach the next step. So you can't waste time on activities that are not fulfilling your targets. Yeah? You can't waste time doing, let's say, scientific analysis of every sample that you have. You need to start prioritizing a bit where your focus is. And that is really the key driving point, that you have to jump the spectrum. You have to jump from a low-risk environment in academia to a high-risk environment in startups. That shouldn't deter you from doing it. You just have to think about that and incorporate this in your strategy. And what the best way of doing is to really start assessing, making a proper R&D strategy and a budget. You know, what can I spend money on? What can I cannot spend money on? Where is my technology standing right now? What are the milestones I have to hit? For example, for my investors and for my grant application. What are the KPIs that substantiate this development, this maturity? For example, stability or quality grade. What are development steps? For example, testing, etc. Characterization that I need to do to support that, and what's only just nice to flag. Say, for example, imaging. If you don't need so many images, and then learn to delegate. So what do I really have to do myself still, and what can I delegate to vendors or third parties? If you don't have all the analysis equipment in your lab, send your sample to a lab, to a different lab, to be qualified and characterized. You will pay money for it, but you don't have to worry about it, because it comes back with a report. So you're winning time. You're moving forward. And that's practically my takeaway for this piece is, your way of working must shift. You're still in the same place, in the same lab in the beginning, but you have to think differently. And startups and R&D are very different points, but there's a lot of people doing it, so you can learn from them and see how they approach things. And last but not least, before we go into Q&A, 3 books or 3 types of books that I wanted to recommend for anybody thinking about going into startups or starting one. The first one, without making any commercials, is from one of our advisors. He wrote a book, From Science to Startup, in which he described his experience as a businessman working with a group of researchers to develop and commercialize a technology. It's a very interesting read because it sheds a bit of a light on how researchers get tangled up with science while they actually should think about product. And that's some of the pitfalls that anybody of us will fall in. The second one is the Dear Female Founders, a recommendation from our CEO. I think a very good book, helping also from female entrepreneurs. We have, luckily now a growing number of women finishing higher degrees in education across the globe, also pushing more into running technical deep tech startups. And again, there are certain hurdles you have to overcome. It's never easy. And it's important to support that, and there's materials around it, and I think it's a good read. That's why I want to recommend it. And the last one for our work week is, I think, the most famous book of these type of books regarding efficiency and effectiveness. There's many others that you can look for. As I mentioned before, your time is valuable. So now every hour of creative time that you spend doing something somebody else could do for you in a startup is an hour lost. You really have to figure out where you want to spend your time as a CEO, as a CTO, as a researcher. You want to do the most effective that you can do to drive the development of your product. You don't want to stick around doing analysis that you can just simply pay somebody to do for it. That's the quintessential point. With this, I would like to finish. Thanks a lot for listening in. I hope you enjoyed the lecture. I hope it wasn't too fast, that it wasn't too cramped. On the right side, here's a picture of Konstantina and George next to our current lab scale reactor, still down in the catacombs of ETH Zurich. With this, I want to give back to Olivia and open the Q&A.
Hi, Max. Yeah, thank you for the comprehensive overview on the company as well as yeah, what it takes to commercialize. Yeah, that was great. Um, does anyone have any questions to start off this Q&A session?
I guess I can go first. Thanks, Maximilian, for that really, really great talk. And it's nice to see, you know, someone attempting to solve this huge, huge problem, because chemical manufacturing is really difficult, I think, to have any kind of company, and or what about a spin out. So I guess my question, since I'm also involved in sort of like scale up as well, is you know, as a growing company, how are you you know, sort of doing scale up? Because you said these, you know, timelines, you know, going 1,000K by next year, 1,000K by next year, because that's a huge fundraising ask, I think. So and it's also a technical challenge, particularly today with all the procurement, you know, sort of hurdles. It takes like a year to get anything. So how do you address this challenge?
Yeah, that's a good question, Nicholas, and that's why before I said it was an ambitious timeline. You know, looking at the years, it's very ambitious. The first thing is you have to find the right strategic partners and vendors. So we started with doing the lab work, and then we early enough contacted engineers to do first conceptual engineering. So do a first flow sheet, do a first calculations of what could be the issues in the system. And then in parallel, we're now working with a couple of research institutes that have the different equipment that we need. So there's still research institutes out there, believe it or not, that run distillation columns with 200 liters, or that run an extractor with 50-liter volume, that you can then use and say, hey, we've done the simulation, let's verify if that works. And that equipment already would be about the size that we need for a pilot plant. So we are practically starting to check if what we ever get as a model solution, we can test there. So for example, when we now do distillation in a couple of weeks, we are not using the actual product that we have. We are basically putting together a solution, a mixture of what we know comes out of our reactor, because we cannot make 10 liters. We can make now 2, 3, 5 liters, but we can't make 10. So we had said, okay, we're not going to wait now for 1 month to make 10 liters to give them for distillation. We just make a model solution, we test it, because in the end it's chemistry, it works the same. It's enough to prove the point. So there's some shortcuts you can take like that. And then once we have these verifications, there's a lot of companies that actually will build the pilot plant for you. So you have to then basically ask them for offers. They give you back a number, and then you go to your investors and say, look, the pilot plant will cost us X million to build, and that's the timeline, and that's the point, and we're going to ask you for so much money, and we think that's our target valuation, and then you negotiate out. That's until the point, until the proof of concept of the pilot plant. That's how you go. And then for the commercial plant, it will become different. It's a big step up, as you said, with a lot of money raising, because then the amount of investors that can lead such a round are very limited. But when you look around, there are a lot of companies and a few companies who have managed it. And there's a lot of funds now in Europe and in the US who actually lead these rounds and give money to such kind of, it's called Series A or Series B rounds, that come in and say, hey, we talked to a few of them. They say, look, we don't invest below 100 million. And then we bring in other investors. And these guys, they do a full due diligence on your process. They bring a lot of experts to just check if you're actually, you know, a real asset, a real innovation. And if they say yes, you will get the money to build the plant. Because if you then also, don't forget, you basically go then from zero revenue up to full load. Because if your chemical is a biochemical right now, you're gonna sell the full volume, pretty sure. So this upside will practically give you the valuation that you need to move forward, that you can actually then go to the right scale. The question will be, as you said, the timelines. Right now, I would always discount a bit for a couple of months, but I think by the time that our technology or others at our stage are ready for commercialization, we might be beyond the point of the issues with supply chains. Was this helpful?
Yeah, that was a great answer. Thanks very much for that.
Welcome.
All right. Just having a look at the chat box. Does anyone have anything to add? I see there's quite a few Biosimo people in the conversation as well.
Yeah, I made them all join.
Yeah. I guess just for me, I was just interested to know how your time is kind of divvied up nowadays, because you mentioned that if there's something that you can do to pay someone else, that they do that. So how much of your time is split between the lab and how does that look like?
So I'm currently transitioning from the day job I was still running until now into full-time in the lab. That's also something that as a researcher, or when you come back from industry, you have to account for that. You often can't do the 100% switch from one day to the next. I spend 1 day a week in the lab, supporting the team, having discussions. I personally haven't really touched the reactor in a while, I think a couple of weeks, but I'm usually there for troubleshooting if it's needed. I spend most of my time talking actually to our third parties. So the contract engineers, the collaborators we're working with. Usually I work with them and say, okay, how are we standing, what we're doing? And it's great because we get a lot of things done. And most of the time I spend coordinating with them what they're doing for us.
Yeah, that's interesting. And again, very different to just being purely in a academic research. I think if no one has anything to add, we might end the talks here.
Yeah.
Yeah.
Thanks for inviting me.
I just would like to thank Max again. Thanks so much for your enlightening lecture for me. I probably will watch it again. And especially the idea of shifting your role from academia to entrepreneur. I see that you are ready to yourself, convert yourself to a proper entrepreneur. Thank you so much. If I have any questions, I can always reach out to you and ask.
Yes, exactly. I mean, to everybody on the call, if you have a question, anything, if you don't have my email now, you can go on our webpage. You can reach out to me and the team, and we are happy to answer any questions you might have. So thanks again for inviting me, Zhen and Olivia.
Yeah. Thank you very much, everyone, for attending. It's a good turnout, and if you're a CARES person, this will be uploaded to the CARES intranet soon. So just watch out and keep an eye on it. So thank you, everyone.
Thank you.
Okay, thank you.
Bye.
Bye.
Bye-bye.
Yeah.
Nice to meet you.